Uh, So for today's review session, we're gonna start with the alkene reactions, where the first reaction is hydrogenation, and then we're gonna go all the way up to hydroversion oxidation, right? So for the reactions of alkenes, there are 4 things to look out for: stereochemistry, RNS, regional selectivity, Markovnikov versus anti-Markovnikov, and we'll go over what that means as well when we get to the reactions. Stereoselectivity, so the reactions could either have a property of syn addition or anti-addition. Pascal calls it like a syn facial attack or anti-facial attack, but it's more commonly known as syn addition, right? But if you see that on the exam, that's what this basically means, because I heard him say this in lecture. And then also if there are any carbocation rearrangements in the reaction or not, right? So for stereochemistry, let's go over the difference between enantioselectivity and diaselectivity. A reaction is going to be enantioselective if that reaction forms products that are enantiomers of each other, right? And do you guys remember what is the name of that mixture if there's a 50-50 racemic mixture, right? It doesn't have to be racemic mixture though. Like let's say there's a 60-40 mixture of enantiomers. But if there's 2 enantiomers, that reaction is still enantioselective, right? For diastereoselectivity, a reaction is diaselective if it forms products that are diastereomers of each other. And do you guys remember how to tell if 2 molecules are diastereomers of each other? Like what has to happen with the chiral centers? All of them or some of them? Only some of them, right? In enantiomers, it's when all of the chiral centers are inverted. For identical, none of the chiral centers change at all. All of the chiral centers stay the same for identical, right? Now let's go over relative stereochemistry versus absolute stereochemistry. So absolute stereochemistry is talking about molecules as a whole. So they will have a set R and S chiral center where like the molecule could either be dextrorotatory or levorotatory, and we determine that through lab techniques. Relative stereochemistry is more about like the reaction where when, let's say, for example, we have this alkene, like let's say right here, and okay, let's say we react that with Br2 CCl4. Okay. So we'll go over this reaction in detail later, but what you will get as a product are these right here. Right? But I'll go over the mechanism of this when we get to this reaction. Say, but right now I'm just gonna write out the products to determine to explain the relative stereochemistry. Okay, so what are these molecules in relation to each other? Are they identical enantiomers or diastereomers of each other? Diastereomers, right? Because these 2 chiral centers here are flipped, but that chiral center right there stays the same. So this is relative stereochemistry because the only thing that reacted is this alkene right here. Nothing touches this carbon in the mechanism, which we will go over. The only thing that reacts is that double bond right there. Double bond was relative to this portion of the molecule. And that's relative stereochemistry. Where like this could be like, I don't know what it is yet, but like R or S, the other one is gonna be like S and R, relative to whatever the stereochemistry is here, right? Yeah. If the reaction creates diastereomers, then it has relative stereochemistry, yes. And it's also diastereoselective if it creates diastereomers. Right. Okay. Now let's go over hydrogenation right here. So let's say we have an alkene, like say this right here. When we put that alkene through H2 and some kind of metal catalyst, you can see different types of metal catalysts. You can see PDC, you can see PT, or you can see rainy nickel. All of these are just metal catalysts that catalyzes this reaction, right? What that does is that it will add hydrogens onto the carbons of the double bond here. Right? An important thing is that this reaction does a syn addition. So the hydrogens will attach on the same side. Right? Where I put the hydrogens on the alkene here on a wedge, so they both have to be wedges because this reaction does a syn addition. Right? The product that we get from this is an alkane because we converted this alkene to an alkane by getting rid of that double bond and adding hydrogens to each carbon of the double bond. The stereoselectivity of this reaction is going to be syn addition because the hydrogens attack on the same side, the same face, syn facial attack, syn addition. The regioselectivity of this is none. There is no regioselectivity because we are adding two of the same groups on the alkene, hydrogen and hydrogen. So there's no Markov-Markov or anti-Markov yet, right? The intermediate of this is going to be a single hydrogen transfer. Right? Where the mechanism I'm going to show right here. So let's say our H2 looks like this, where one H is red and the other H is blue. And our metal catalyst is going to be right here. Let's say that is PDC. Okay. The H's are going to attach to the metal. Where we have one red H and a blue H here. Okay. And now this is where we bring in our alkene, where our alkene is going to be this reactant that we started with in the beginning. Right? One of the H's are going to attack the alkene. When that happens, at the same time, that double bond there is going to attack that metal and attach to that metal right there. So now we are going to have, let's say, the red H is now attached to this carbon. And I'm going to put the wedge, the methyl as a wedge, and then the hydrogen as a dash. And then that carbon there is now bonded to that catalyst. And let's say this is a wedge. Let's say this is a dash. Now, the other thing that's going to happen is that this blue hydrogen is now going to attack the other side of the alkene. And then the bond that is attaching the alkane to the metal breaks off to the metal catalyst. And that gives us this product here, where we see that the red and blue hydrogens were forced to attack on the same side of the alkane, because once the red hydrogen attacked that alkene, the double bond was forced to make the bond between that metal and the alkane right there. When that happened, this hydrogen here is forced to attack on the same side as that red hydrogen, because that position there is locked once this step happens, because this happens simultaneously. when the red hydrogen attacks the alkene, the double bond attacks the metal at the same time, which locks that red hydrogen in place and forces this blue hydrogen to attack on the same side as the red hydrogen, which is why this is a syn addition reaction where both hydrogens attack on the same side. So if you draw out the product and you draw them both as wedges, one as a wedge, the other one has to be wedge. If one hydrogen is dashed, the other hydrogen has to be dashed as well. This is a syn addition. Right. Okay. So an example that you might see on the exam is something like this, where you have H2 PDC. We know that all we are going to do is get rid of that double bond and add hydrogens on the same side. So let's say we put the hydrogens as a dash. If we put hydrogens as a dash, like that, that forces this methyl group to become a wedge, like that. Right? You could have done it the other way as well. If you chose to make that hydrogen bond a wedge, that would also have to be a wedge as well, because this is an addition. That means that this methyl would have to be a dash. But that's the same exact thing as this, because there's no other sterocenter. So like you just flip it upside down to get the same exact thing. Yeah. Yeah, so this one doesn't have to have plus enantiomer because there's no chiral center here. This carbon here has two of the same groups. So we don't have to do plus enantiomer. If this was a chiral center, like let's say I added isopropyl here, isopropyl here, then you would have to do plus enantiomer. Yeah. Where the enantiomer version of it would look like that, right there. Right? But since that wasn't there before, the wedge, the dash version of that is the same exact thing of this. It's just flipped upside down. Yeah. Another thing about this reaction is that it is going to prefer the less hindered side. So let's say that we have something like H2 BT. Okay, and instead of H, you can see D2, where D is deuterium ion, which is an isotope of H. The reason why professors like to do this sometimes is because in the product, you have to draw out the Ds. You can't imply it as invisible because all the other H's are invisible. So when you just draw out the product, you could just get rid of that double bond and then say that's the answer. But if your professor wants to test you on the stereo selectivity of this, where would the Ds attach onto this alkene? Would it attack on the top side or bottom side based on what's around this molecule? Yeah, the bottom side, because there is more steric hydrogens on the top side, blocking the D2s from attacking on the top side. That's right. So the answer here would be that the Ds would attack on the bottom side because is less steric hydrogens there. This is the major product. The minor product would be if the Ds attack on the top side, making them both wedges. Right. So the minor product would be this. Because of steric hindrance. Minor. Steric hindrance. Okay. Now, when we do these reactions give off heat of hydrogenation, which is a form of energy. So these are the stability of alkenes, where this is talking about the hyperconjugation. The less substituted the alkene is, the less stable it's going to be because of hyperconjugation. The more substituted the double bond is, the more stable it is because of more hyperconjugation. Right? We have three different di-substituted double bonds: the cis, geminal, and trans. The cis and geminal alkenes are similar in stability, but the trans alkene is going to be more stable than the cis and geminal alkenes. Right? So if an alkene is more stable, it will have less energy, less potential energy. If an alkene is unstable, like more unstable, it will have more energy in the form of heat, right? So this is in Mescal's lecture notes right here, where we have some kind of alkene, random alkene. We put that through H2 catalyst. It gives off some kind of heat here, right? And it gives off a bigger magnitude of heat if it's more unstable. This alkene here is more unstable than these alkenes because of steric hindrance. That symbol there is steric hindrance. These bulky terbutyl groups are close to each other, and this is also cis as well. This cyclobutane ring is more unstable than this cis alkene because of ring strain. Like, let's say this carbon here, right, is sp3 hybridized. Do you guys know what's the preferred bond angle for sp3 hybridized carbon? Yeah, 109.5. It prefers to be in the 109.5 degree, but it is locked in the 90-degree bond angle, right? So now let's look at the cyclopropene. This carbon here is also sp3, but it is locked in the 60-degree bond angle, right? 60 degrees and 109.5 is a bigger difference, which is why this cyclopropene here has bigger ring strain, because there's a bigger difference between 60 and 109.5. Cyclobutene here has smaller ring strain because there's a smaller difference between 90 and 109.5, which is why this cyclobutene is more stable than that cyclopropene. And this cyclobutene gives more energy. This cyclopropene gives less energy. Wait, it's the other way around. This cyclopropene gives more energy because it's unstable. This cyclobutene gives less energy because it's more stable, right? So think of it like energy and stability are inversely related. The more stable the alkene is, the less energy it gives, and the other way around as well. The less stable the alkene is, the more energy it gives off. They're inversely related. Right? So this cyclopropene here would be higher in energy than the cyclobutene. Yeah, less stable, release more energy. Okay. So in this reaction here, the benzene does have alkenes, but those alkenes will not react because that would break the aromatic structure of the benzene ring, which is stable. And we don't want to break that stability. We are going to react it with this alkene here that is not in the aromatic ring, right? So that's why when we react it with H2PDC, that alkene disappears because the hydrogen is attached to here and here on the same side, right? And the reason why he drew this bond out as flat and planar is because this could be a wedge or a dash. We don't know, right? It could have been R or S. But if you use some kind of specific catalyst, you could prefer the R or S product, right? This depends on the catalyst that you use. And this right here is an enantioselective reaction, because if you use a specific catalyst to prefer one enantiomer over the other, like in this case here, he used a catalyst that adds the hydrogen on the dash, right? If it locks the hydrogen on the dash, this is enantioselective because it selects for this enantiomer. This reaction here that has the regular PDC catalyst, that was not enantioselective because it could go like either or way, right? Say, And here's the equation for enantiomeric excess, EE, where it is going to be equal to the percent of the correct isomer you want minus the percent incorrect isomer you don't want. This was like a new thing like I never learned about in 119B, but this was brought up in lecture where you might need to know it for the exam because he might give you numbers like the percent number of the correct isomer is that, percent of the incorrect isomer is that, where you just have to plug in the numbers for that equation, right? Because if you wanted one enantiomer over the other, but you have 50% of one enantiomer, 50% of the other enantiomer, 50 minus 50 is 0% EE. So if you have 0% EE, that means that you have a racemic mixture. Yeah. Yeah, so that one, he would have to tell you that. Yeah, he's gonna tell you that. Like, because the catalysts are really big, bulky molecules, and that's like used in like current research. Like now, yeah. Okay. So this is another perspective on hydrogenation where it requires a metal catalyst such as PDC, RH, nickel, or PT. Okay, where here's the like the most basic example. You just put H2, some kind of catalyst, and then you get rid of that double bond and add two other hydrogens on that double bond right there. Right? And this is also syn addition. So let's say we have a more complicated alkene with some kind of center that would give us a chiral center. H2 PDC. For this reaction here, the hydrogens could attack on the top side. So let's say they are both wedges. Both hydrogens are wedges. That forces this methyl group here to be a dash. Right? The other product that you can see is the enantiomer version of that. Like let's say the hydrogens attack on the backside, the dash instead. That would force this methyl group to be a wedge like that. And this right here would be a 50-50 mixture of enantiomers, which is a racemic mixture. And an example of a catalyst that prefers the R and S, like one enantiomer over the other, is this dipamp catalyst here. You don't need to know about that, but you just need to know. It might be a conceptual question, like how can we prefer one enantiomer over the other? And then they have to say using a specific catalyst that prefers that enantiomer over the other. So that's more a conceptual question. Yeah. Uh, yeah, right, right. For them to be diester selective, it would need to have another chiral center, like let's say that right there. Then these would be diastereomers, diacellular selective instead of enantiomer selective. Yeah. Yeah, if already pre-existing chiral center already exists, it could affect like the stereochemistry of these two products. But the pre-existing chiral center will not be reacted if it's not a like reactive group. Like if it's just an alkane like that, then it stays unreacted all throughout the reaction. Okay. So let's say we have this alkene right here. What do you guys think the product will look like here? Yeah, it would form two stereocenters. And how many products would we get here? like let's say two, right? Because the hydrogen could be a dash or it could be a wedge. And these two answers here are enantiomers of each other. Okay. These are the two products that you'd get here for this reaction. You don't have to draw out the hydrogens specifically. You could have also drawn it like this as the answer for predicted products with just the R groups. But make sure they are syn to each other on the same side. Yeah. Yeah, so this product here, when one hydrogen is wedge and another hydrogen is dash, will not happen because this reaction is always syn addition. The H2PDC hydrogenation reaction always adds hydrogen on the same side. So if one hydrogen is wedge, the other hydrogen has to be wedge. If one hydrogen is dash, the other hydrogen has to be dash because of this mechanism here. The metal locks the hydrogen into place for the other hydrogen to attack on the same base. Syn facial addition. So this product here would not exist. This here does not exist. Yeah. Yeah, so that is when he asks you how many possible stereoisomers are in, like, how many possible stereoisomers are in this molecule, right? But in lecture, he said like the number of possible isomers would not equal to the number of stereoisomers because of relative stereochemistry. Like, you know how if there's a pre-existing chiral center and that pre-existing chiral center does not react at all, it doesn't change at all, right? So it just stays there. So that's why you don't get all of the stereoisomers because only some of the chiral centers change, but not that pre-existing one that is unreacted. So that's why you get less than the number of total like theoretical stereoisomers. I'll show you an example of that when we get to that that part. Yeah. Yeah, these two are enantiomers of each other. And this would be a racemic mix, 50-50. Now, let's try these practice problems here, where there's 5 different molecules here, and you have to rank them in order of increasing heat hydrogenation. One is going to be giving off the highest heat, and then number 5 is going to give the lowest heat. Okay. So try that for 5 minutes, or say 3 minutes. Thank you. Have you guys signed in yet? Oh, okay. Yep. Thank you. Thank you. Yep. All right. It couldn't be one wedge, one dash because in the mechanism, the metal, it could be PDC, PT, or radium nickel, right? That locks the hydrogen in place. So when the first hydrogen gets added on the alkene, right? The alkene is locked into that same phase as the metal, and then the other hydrogen will attack on the same side as that first hydrogen. So I'll show you that right now here. It's where the mechanism of that reaction is something like this. Well, you know how this is the H2 PDC. The first thing that happens is that those H's attach onto the metal like that, right? And then one of the hydrogens attach onto the alkene like that, and that means the double bond attaches to the metal at the same time. When that happens, this locks the alkene in place, where when the other hydrogen attacks, it has to attack on the same side as the red hydrogen. Right? So if one hydrogen is wedged, the other hydrogen has to be wedged. If one hydrogen is dashed, the other hydrogen has to be dashed. And that's called syn addition, where they add on the same side. Yeah. Yeah. Uh-huh.
I differentiate between the two because these are both monosubstituted and these are both disubstituted, but are these both trans, the hydrogens?
Yeah, these are both trans. That's trans, that's trans.
So would they be equal, or is there something?
Yeah, so there's something else. There's one that could do resonance. There's one that's conjugated. There's one that's not resonance.
Oh, resonance.
Yeah. Uh-huh. Yeah. Yeah. So what kind of alkene will give us the highest energy? An unstable alkene or a stable alkene? Unstable alkene, right? And there are three different factors to think about when you think about stability of alkenes. There's hyperconjugation, right? There's conjugation, and there's E and Z, where E is more stable than Z, right? More hyperconjugation or more substitution means more stable. More conjugation or more resonance means more stable. So first, I think the easiest thing to think about this question is look for your most stable alkenes. Which one of these alkenes looks the most stable to you guys? Yeah, the one on the very left, because all three of these are conjugated and they can do a lot of resonance with each other, right? Since this has the most amount of resonance, this is the most stable. If it's the most stable, will it give us the highest or lowest energy? Lowest energy. So this, the one on the left, is number 5. So don't think about it like, since it's the most stable, it's number 1. Well, it depends on the question. If the question asks which one's the most stable, then this will be number 1. But the question here is asking which one is going to give us the highest energy. Where since this is the most stable, this gives us the lowest energy. So make sure to read the question carefully. Right. Now, let's just look at the most stable ones first. The most stable ones are the ones that can do resonance. We could automatically get rid of this and this alkene because of the sp3 roadblock right here. Since this carbon is sp3 and these carbons are sp3, they block resonance between these two double bonds, right? So we do have resonance here and resonance here. Since they have the same amount of resonance, the next factor we look at is hyperconjugation, right? Which double bonds look more substituted to you? Yeah, the one on the right, because this double bond is di-substituted. There's 2 R groups attached to it. This double bond is also di-substituted. But this double bond here is mono-substituted. And this double bond is di-substituted. So that makes this system more stable than this system here due to more substitution, more hyperconjugation, right? So that makes this number 4 and this number 3. Any questions on this one? Okay. Now let's just assign one of these as the highest energy. Which one looks less stable to you? Yeah, the right one, because this double bond is mono-substituted. This double bond is also mono-substituted. Whereas this double bond is mono-substituted, but we have one di-substituted double bond here. So the right one here is less stable, giving off the highest energy. So that's number one, right there. And that's number two. 1, 2, 3, 4, 5. Right. So the first thing that I did was that I determined which was my most stable alkene, which is this one that can do a lot of resonance and has the most amount of double bonds that can do resonance with each other. So since this is the most stable, this gives us the lowest energy. And then I got rid of the ones that cannot do resonance at all, which is this one and this one, and I ignored that for now. Then I compared those two, where I determined that this is the more stable system because both double bonds here are more substituted than the two double bonds here overall, right? Because this double bond here is only mono-substituted, whereas both double bonds in this case, they're both di-substituted, right? And then I just determined which one's less stable here, which is this one because they're both mono-substituted, which means that since it's the least stable, this gives us the most energy. Any questions on this question? Let's move on to the next one. Oh, yeah, I'll add you. How did you hear about this? Oh, I see, I see, yeah. I'll add you to the canvas, yeah. Yeah. On the canvas, I post like the outline of these notes, the field notes, and also the recordings of it as well. In practice. Yeah, I follow my scouts notes. And also I use other notes like Helix's notes, the series notes, combine them, yeah. And when I make the practice midterm for you guys for midterm one this weekend, I'm gonna combine them from the series, Helix, Levens, and yeah, he doesn't give practice. He just doesn't like look at the textbook.
Yeah, that's what I was doing. I read
Yeah.
chapter 12.
Oh, all of it already? All of it.
But it was a lot.
Yeah,
Then I found out about that.
yeah. See,
It's just not
yeah. We'll just click add people. Oh, yeah, here it is. Oh, and then UC Davis email. Hello. Oh yeah, yeah, to the canvas. Yeah, how did you guys hear about? Oh, what was their name? Oh, shoot, never mind. Sorry, sorry. Yeah, yeah. There you go. Just add your UC Davis emails in there.
Okay.
Yeah. Okay. Um, which one of these double bonds are the most stable? Which one of these systems are the most stable? Yeah, the first one. And why is that the case? Yeah, most resonance. That's right. Because all of these three double bonds here can resonate all throughout the ring. Right. Now, the other thing is to look for the least stable double bond. Which one of these is the least stable double bond? So now let's okay. Try these two practice problems and then don't do these ones here. These ones will just be extra practice. Just do these two and then we'll move on to the next reaction. Oh yeah. Yeah. Thanks for letting me know. Please me too. I gotta find other people then too. Uh-huh. Oh yeah, the canvas. I'll use the canvas. Yeah. Uh-huh. Yeah. Signed in. Yeah. Oh, okay. Yeah. Yes. If there's no consensus formed, you could leave the answer as that.
Okay.
Right. Yeah.
There's scenic or not.
Oh, right. So in this case, right, they are not enantiomers, so you don't have to say racemic because racemic is a mix of enantiomers. They are diatomers because only these two characters change, but these two characters stay the same.
Oh, okay.
Uh-huh.
Okay.
Right.
Wait, so diastereomers, it means that, oh, okay.
Yeah, some change, but some don't.
Okay.
Yeah.
So
And there's one major one and there's one minor one.
okay.
Uh-huh.
So,
Yeah. That's the hindrance. That's right. It's safer to just put that, but if you do include both, make sure to label it so that they don't take points off from you. Yeah. Yeah.
So, like you specified stereochemistry
Mhm.
of these two, then would it be possible, like, would there be one where you don't have the stereochemistry and then you just like you decide, I guess,
Yeah.
and still make it that they attack from
Wedge or
opposite,
dash.
yeah,
Yeah.
like the bottom. Like I wrote it out like this,
Mhm.
and I also wrote it out like
Yeah.
this. Sir, is this incorrect?
Yeah, this is incorrect because it's set as a wedge in a reactant, which nothing happens to it, so it has to stay as a wedge. If it was a flat bond, then that would be a potential answer, right?
Like
Which,
since here it's specified, we
Uh-huh.
would just give this one.
yeah, that's right. Well, that's the major one, and the minor one would be if these were wedges.
And then, would there be a question where these are on opposite, so this is wedge and this is dash for this one, or would it only be
So there could be a question like that, like if this was wedge and this is dash, right? And let's say that wedge was just a methyl group. Let's say this dash was a trig-butyl group. You go for the side that is less sterically hindered, which is the red side, because the wedge side has the smaller methyl group.
right?
So that could be a tricky question that Mascal can give. That's actually a good question. Yeah.
But they wouldn't be the same.
Yeah.
Probably.
Yeah.
So
Well,
it's like the same steric hindrance, or yeah, steric hindrance. So then,
right. Because if it attacks on the more sterically hindered side, that's gonna be the minor product.
right.
Right. We want to attack the less sterically hindered side.
Okay.
Yeah. Yeah.
Related. It's about osmosis.
Oh, it's analysis. Yeah.
Yeah. Oh, is this a reducing agent? The CH3.
COH. That is.
Oh wait, no, this is not osmosis. I had two questions. This was from the dihydroxylation.
Hydroxylation, yeah.
Yeah.
You don't need to know the mechanism for the second step. Like Mystery doesn't go over it, Helix doesn't go over it, like no one goes over that. Yeah.
You know about what zinc does in osmosis, where you
Uh-huh.
just assume that it just takes oxygen from CNO and then you have products.
Yeah. Well, I'm not too sure the mechanism. I have to look back at it and then
Okay.
review it. But yeah.
Okay.
Yeah. But that's the end of the chapter 12 reactions. That was an analysis one. Yeah. Okay. So where would the deuterium ions add? Which face? The top face or the bottom face? Yep, the bottom face, because it has less steric hindrance. And they both have to be dashes because this is syn addition. Right? A good question that popped up earlier was, let's say instead of that, we have something like this. Let's say it was wedge, and then the same thing, D2 PT. Where would the deuterium ions attack now? It would change to wedge. Yeah. Before it was dash, but now it's gonna be wedge. Right? Wedge, deuterium. Because we still want to attack the less sterically hindered side, right? On the top side, we just have a methyl group. On the bottom side, we have a trig-butyl group. Since the trig-butyl group is bigger, there's more steric hindrance on the bottom side. So that's why the deuterium ions would attack the less sterically hindered side, which is the top side there. So this would be the major product for this problem here. Yeah. It's still syn addition, and it still attacks the less sterically hindered side, but it's just different groups. Okay. And for this one here, let's just add hydrogens everywhere, where we do have one chiral center, which is this chiral center right here. And if we decided to add the hydrogen as a dash, then that's supposed to be a wedge. It could have also been a wedge. The hydrogens could have been a wedge, forcing the methyl groups to be a dash. Right? The reason why I didn't include stereochemistry for this carbon, for the product, is because that carbon there is not a chiral center. We only include wedges and dashes on chiral centers. This is not a chiral center because we have two of the same groups, two methyl groups. Right? This one here is also not a chiral center because there's two hydrogens. This one here is not a chiral center because there's two hydrogens, but this one is a chiral center. So that's why I had to include stereochemistry there. And what are these to each other? Enantiomers, diastereomers, or identical, or meso, or constitutional? Yeah, enantiomers, right? Because we only have one chiral center where that one changed completely. Yeah. And this is 50-50 enantiomer, so we could say racemic mixture, but you don't have to. Okay. Let's move on to the next reaction. Okay. So a common theme for most of these reactions is going to be something like this right here. We know that an alkene can have a negative charge and a positive charge. We know that the carbocation stability increases when it's more substituted. So which one of these carbons of the alkene here is going to be giving the most stable carbocation? The left one or the right one? Yeah, the right one, because the right one is more substituted, right? So we know that this double bond here can do resonance. Let's remove that double bond onto that carbon right there, right? And we want to do it in that way because how many electrons are in that bond right there? How many electrons are in one bond? 2 electrons, right? So let's say that we move that bond or those 2 electrons onto this carbon. That means that this other carbon here lost the bond. Before it had 4 bonds, 1, 2, 3, 4, but now it only has 3 bonds, which is why it's now going to be positive charge right there. We did it this way to give the more stable carbocation intermediate. We don't do it the other way. We don't put the negative charges on this carbon because that would give us the less stable carbocation, right? Which means that the basic or nucleophilic carbon is going to be the less substituted carbon right there, right? And that's going to be a common theme for a lot of the reactions that's going to come up, right? Where we want to form the most stable carbocation intermediate. Right? Okay. So let's say we have the same thing here, and let's say that we have some kind of electrophile bonded to like some kind of nucleophile, right? We know that this carbon here, the less substituted carbon, is the nucleophilic carbon because we want to form the more stable carbocation. If we want this carbon to be the carbocation, we want that one to lose the bond. So that means the other side of the alkene will have to attack the electrophile and kick out some kind of nucleophile. Okay. When that happens, that carbon there is now bonded to the electrophile, and this carbon on the right lost the bond, which is going to be the carbocation there because it lost the bond. This nucleophile here gets kicked off as the electrophile is attacked. And the nucleophile gets kicked off as a nucleophile minus, where that nucleophile there is just going to attack that carbocation right there. Okay. And this right here is the Markovnikov rule. Markovnikov rule. Okay. Where the nucleophile attacks on the more substituted side of the alkene. This was the more substituted side of the alkene, and we see that the nucleophile attached to the more substituted side of the alkene. The electrophile attaches to the less substituted side of the alkene, and that's also the Markovnikov rule. You can think of it as either way or both ways. The way I like to remember it is like the nucleophile attaches to the more sub side of the alkene. That means that anti-Markovnikov is going to be the nucleophile attaching to the less subside, but we'll get over to anti-Markovnikov once we get to hydroversion oxidation and radicals. Okay. These are Pascal's notes right here, where he said that A is the electrophile or nucleophile, and B is like the other thing. The alkene there, just like one carbon of the alkene gets a bond with A, the other carbon of the alkene gets a bond to B. Okay. And before in the reactant, we had 2 separate molecules, 1 and 2, right? But then when this reaction happened, we combined them to make one one product. 2 to 1, that decreases the entropy because we're creating order. Like before there were more molecules, there were 2 molecules here, but now we reduce that to 1. That's more order. So this is unfavorable in terms of entropy, right? But you guys remember how when the alkene like gets broken, it releases energy in the form of heat. The energy that gets released in the form of heat is high enough for this reaction to be favorable, right? And that will make this reaction overall favorable because this we here will overpower that number there. Okay. So here are the upcoming reactions that we're gonna learn about. We went over hydrogenation already. Now let's go over hydrohalogenation. Okay. So let's say we have something like, let's see, let's make this a little, yeah, do that, alkene there, and put HBr. This could be HX, where X could be Br or Cl. Right? The very first thing that's going to happen is that we have to protonate the carbons of the alkene because we have a strong acid, right? We said that this carbon here is going to give us the more stable carbocation. That means that we want this carbon to attack the hydrogen, right? So this carbon here is going to attack the hydrogen and then kick out the Br. Wait, that's going to be the mechanism. Let's do that in the mechanism. HBr. Carbon attacks the H, kicks out the Br. And then this is the intermediate we get right here, where this carbon gained the hydrogen, this carbon lost the bond, gains a positive charge. Okay. From there, the Br minus that got kicked out will attack the positive charge right there as a nucleophile. Okay. We do not want to do something like this. Like we don't want this carbon here to attack the hydrogen and form this carbocation here. The reason why is because it's a less stable carbocation, which is going to give us the minor product. Right. So this one here, minor. This one here will be major. Because this one here has the more stable carbocation intermediate. Right? That's the most important thing, like the carbocation intermediate. Well, we want that to be the most stable. It could get trickier if there's a possibility of a hydride or methyl shift. And we'll go over those examples too. So the product for this is that, and the mechanism is shown there. Script. In this case, yes, it will always be racemic, but because this right here, when it attacks, it could become a wedge or dash. But if there's a pre-existing chiral center, like that, then this would no longer be racemic, but they would be diastereomers. Because racemic mixture is a 50-50 mix between enantiomers. If there's a pre-existing chiral center somewhere else in the molecule, then you are going to get these two diastereomers here, right? Which these are not in racemic mixtures of each other. Yeah. Mm-hmm. Okay. So the product for this will always be a haloalkane. Right? Because we added halogen onto the alkane. We created a halogen on an alkane right there, right? And there's no more double bond. the stereoselectivity here, like syn addition or anti-addition, there's none because of the carbocation intermediate. This carbocation intermediate here is flat and planar, sp2, which means that this Br minus can attack on the top side, giving us a wedge product, or the bottom side, giving us a dash product, which is why there's no stereochemistry. There's no anti-addition or syn addition. Because let's say the H here was like grabbed on the top side. Let's say that H was a wedge. This bromine could be a wedge or a dash as well. So it could be syn or anti-addition. That's why there's no stereochemistry, because this is flat and planar, where the bromine can attack on the top or bottom side. It doesn't matter. Right. For regioselectivity, this is Markovnikov. Because we see that the nucleophile bromine attached to the more substituted side of the alkene. That's the Markovnikov rule. The intermediate that was formed is a carbocation intermediate. This mechanism is called electrophilic addition. Because the very first step that happened was that we added this electrophile or hydrogen onto the alkene to form this carbocation intermediate, and then the nucleophile bromine attacks that carbocation intermediate to give us the final answer here. Okay, let's skip all of these slides because we basically just talked about that already, like the Markovnikov, anti-Markovnikov. But go to this slide right here, the addition of HX rearrangement. Okay, so let's say we have something like this with HCl. Okay, which one of these carbons will grab the H from the HCl? Yeah, this one right here, because we want this one to have the carbocation, the more stable carbocation, which means the other end of the alkene will grab the hydrogen. If we want that carbon to have the carbocation, the other end will grab the hydrogen. And that gives us this carbocation right there. Whenever you have a carbocation intermediate, you always have to stop and watch out for rearrangement steps. Look at the adjacent carbons and see if you could do either a hydride shift or methyl shift. Right? In this case, can we do any kind of rearrangement step? Yeah, that's right. Specifically, we could do a hydride shift to convert that secondary carbocation into a tertiary carbocation. Okay. And then we bring in the nucleophile that got kicked out to attack and form our final product. Like that. Yeah. Yeah, that's right. Because the other way you could think about that is that we push those bonds, those electrons onto the very end to create that carbocation right there, where this lone pair right here is the one that is grabbing that H right there, right? But to make everything faster, we just say that that carbon grabs the H, which is basically what's going on here to form that carbocation right there, right? But this is the behind the scenes, what's going on in this step. Right? It wouldn't be the other way. Like it wouldn't be this carbon attacking the H, because if it was, then the carbocation would be here, which is less stable. Now let's try these two practice problems and then move on to the next. Wait, actually, let me make this here. Okay, there you go. Okay, for the first one, which one of these carbons would attack the H? This one's a little bit trickier because they both look equally substituted, but there's one that can do rearrangement and there's the other one that cannot do rearrangement. So which one can do rearrangement? The left one or the right one? Yeah, the right one. But that doesn't mean that this carbon here is going to attack the hydrogen. This carbon here is the one that's going to attack the hydrogen. Right? The other end attacks the hydrogen, breaks the bond between hydrogen and iodine to now form that carbocation. And like we said, this carbocation can do some kind of rearrangement. There's no hydrogen on this carbon, so we are forced to do a alkyl shift or methyl shift. When that happens, this carbon right here used to have 4 bonds, 1, 2, 3, 4, but now it lost the bond. It only has 3 bonds now with a positive charge. Right? And then this whole methyl group just migrated and shifted to this carbon right there. And then from here, we bring in the I- nucleophile that left to attack that carbocation to give us our final answer here. There. Yeah. Oh, right. So if this was a chiral center, we would have to still stereochemistry, but this is not a chiral center because that group is the exact same as that group right there. If let's say it was different somehow, then you would have to show stereochemistry. Yeah, and there would be like enantiomers of each other if there's no other pre-existing chiral center. Like yeah, enantiomers or diisomers, depending on if there are pre-existing chiral centers. Yeah, but that's good. That's good. Yeah. And then the second one is basically what we did earlier. We want this carbon here of the alkene to have the carbocation because it's more stable. That means the other end is going to attack the hydrogen, kick out the Br. That means that this carbon here lost the bond. It gains a positive charge for this Br minus to attack. But first, we have to stop and see if it can do any rearrangements. If it goes here, it's less stable. If it goes here, it's less stable. If it goes here, it's less stable. So there's no hydride or methyl shift here. This Br minus can just attack it right away with no rearrangement step. That gives us that product right there. Okay. Any questions on these two? Yeah. No, usually you don't write minor products for predicted product, where the minor product would be this, but we usually don't write it on the predicted product. If you do write this though, make sure to label it like minor and label this major so you don't lose points. Because if you don't label it, then they might think that you think this is major, which they can take points off for that. Huh? But if you label it as minor, then you're showing that you know that that's minor. Yeah. Okay. And do you know the reason why this is minor? Yeah, the carbocation intermediate is less stable. This comes from a less stable carbocation intermediate. Okay. And then if you guys have the Leaven's chapter 11 and 12 practice, these are like the problems that relate to this kind of reaction. Okay. Now let's move on to the next one. Hydration of alkenes. So let's say we have double bond there, and we react this under acid, water, and heat. The nucleophile here is going to be the water. If you have water, right, then you're going to have an alcohol on the Markovnikov position, the more substituted position. Yeah. Right. So here's the mechanism. We have a strong acid, which means that the very first thing we have to look for is acid-base reactions, because acid-base reactions in OChem are one of the fastest reactions alongside with intermolecular reactions. So the base here is the alkene. Which carbon of the alkene is going to grab the hydrogen, which is going to act as the base? This one? Yeah, the less substituted one, because we want this carbon to lose a bond. So we could use that carbon to grab that hydrogen, kick out the conjugate base, form the most stable carbocation there. In this case, there's no rearrangement to worry about. Where now, let's see which one is going to be our nucleophile. Some people might think that this is going to be the nucleophile because it has a full negative charge and attack that carbocation, right? But this here would not be the nucleophile because that negative charge on the oxygen is really stable because it has a lot of resonance. That negative charge there can do resonance here, and it could also do resonance down here. Since this is doing a lot of resonance, that negative charge is spread out and it's really weak, right? That means that this water here is going to be the nucleophile instead of the conjugate base. The water, oxygen has 2 lone pairs of electrons, where we're going to use one of those lone pairs of electrons to attack the carbocation. Right? That lone pair there is going to attack that carbocation right there. Okay. Now, when we do this attack, there's going to be a new bond between that carbon and that oxygen right there. So you can think of it as like starring the attacking atom and dotting the atom being attacked to track of your groups, right? Because you might add like some wrong carbon or hydrogen, but you know that the attacking atom here is the oxygen, and this right here is the new bond between the star and dot atom. This is the star atom, this is the dot atom. Where we see the star atom, which is oxygen, is still attached to 2 hydrogens, right? So that means that that oxygen there will still be attached to 2 hydrogens. Before it used to have 2 lone pairs, but now it only has 1 lone pair because one of its lone pairs was used up to make the new bond, right? Because one of the lone pairs here is now this new bond that's formed right there. What charge does oxygen have with 3 bonds and a lone pair? Yeah, positive charge, right? Don't forget about that when you do the mechanism, because that's a common mistake. When people draw the mechanism, they always forget to draw the charges there. And you could get like 1 or 2 points off for not drawing charge there for the mechanism, right? So that's a positive charge right there. What's the very last step that's going to happen in this mechanism here? Deprocyanate, right? Using the conjugate base that got kicked out and reforming our acid catalyst, reforming the H2SO4. Yeah, you could use H2SO4 minus or water. Yeah, it doesn't matter. You still get points. Mm-hmm. Yeah. The hydration stuff. Yeah. So for this reaction, the product is going to be an alcohol. The stereoselectivity, there's none. There's no syn addition or anti-addition because of a carbocation intermediate. That carbocation intermediate here is flat and planar, which is why when the water attacks, it can attack on the top side or the bottom side, giving no stereoselectivity because the reaction doesn't select for like doesn't prefer that water to attack on the top side or bottom side, right? It could do both ways, which is why it's not selective. For regioselectivity, this is Markov-Nikov because we see that the nucleophile or the water attack the more subside. Markov-Nikov. The intermediate carbocation. Mechanism, electrophilic addition. Because the very first step here was that we added the electrophile hydrogen into the alkene. Okay. Now, let me give a more concrete example of that here. Say we have some kind of alcohol and alkene like that, plus H2O. Okay. So Do you guys remember the reaction that makes an alkene from an alcohol? There's a reaction name for that. This is one of the preparation of alkene reactions. One of it was E2, and this is the other version, other reaction that makes alkenes. Dehydration, right? Where dehydration, you always start with an alcohol, and then your reagents are going to be strong acid in high temperature. So it could be like 170 to 180 degrees Celsius, but yet you have high temperature. This is alcohol dehydration. So now we have an alkene here, and we want to make the alcohol back. And that reaction was the reaction that we just did, where we created an alcohol from an alkene, right? And this reaction is called hydration. Right? So you can think of it as like dehydration, hydration, they're opposites of each other. Hydration. Where the reagents for that is still strong acid, H2SO4, relatively low temperature, because we want to prefer the SN1 reaction, not the E1 reaction. Because in high temperature, the E1 reaction is favored. In low temperature, SN1 reaction is favored. And also excess water. Because our nucleophile here that was used to make this alcohol is water. So the more water you add onto this side, the more that you're going to go to this side because of Le Chatelier's principle. The more water that is going to overwhelm this alkene and attack the alkene to convert it into this alcohol right here, right? So the more water you have, the more you're going to go to this alcohol here. The less water you have, then the more alkene you're going to have, right? Because this alcohol here came from the nucleophile water. And how can we get more alkene here without changing water? What can we increase? What can we increase to get to more of this? Heat. Yeah, we can increase the temperature. If we raise up the temperature in the flask or some kind of reaction that it's going through, that will favor this this product because of the Le Chatelier's principle. Add more heat here, get to the other side. Add more water here, get to the other side because of Le Chatelier's principle. Any questions on this one? Okay. So it doesn't have to be water that we attach. It could also be, let's say, alcohol. Like let's say we have H2SO4, and instead of water, we have ethanol and heat, right? It's going to give us this product here, where you notice how if we had water, the water would onto the Markovnikov position, the more subposition, as an OH. But if we have an alcohol, the more subposition or the Markovnikov position, we have an OR, right? So let me make that clearer on the notes. Say, we have that and H2SO4. Let's say the water is blue. And let's say some kind of alcohol with some kind of random R group is green. But everything else is the same, acid and heat. Okay. The water will add an OH on the Markovnikov position, the more substituted position. The alcohol will attach OR into the Markovnikov position. Right? So that's the difference. It's the same exact mechanism, same exact reaction, hydration, just different nucleophiles. If you add water in, then you get OH. If you add alcohol in, you get OR. And the R depends on what the R group of the alcohol is. But the same exact mechanism happens. Like pre-existing chiral center, yeah, there could be diastereomers, right? But in this case right here, these like they could create enantiomers if this was a chiral center. Like the way I drew it, that's not a chiral center, so there's no like stereochemistry at all. But if this was a stereocenter and that's the only one, then that would be a racemic mixture of 50-50 enantiomers. Yeah, if this was a propyl instead, then that would be racemic. And if that was a propyl and we had an isopropyl here that was like a dash, then that would be diastereomers. Yeah, then that would be like diastereoselective. Right now, we have no enantiomers, no diastereomers, so no stereoselectivity here. Yeah. Any other questions on this one? Okay, so that was intramolecular. Oh, intermolecular. We could do intramolecular reaction. Like let's say we have this, that. And we put this under H2SO4 and heat. Okay, try this one for 3 minutes. 2 to 3 minutes. Okay. Oh, like it does attack itself. It would attack itself if we are in low temperature, right? Because that is going to do SN1 with itself. But if we have high temperature, then oh wait, actually, if the alkene wasn't there, then it could be polymerization. But we have an alkene there, which is going to be more basic than the alcohol. So that's going to happen. But yeah, that's a good thinking, like polymerization thing. Yeah. Yeah, it is. It is. Yeah. This is going to be done in the presence of just heat and acid. So you you know how if we had water, it becomes an OH, but if you have alcohol, it becomes OR. What is this group here? Yeah, alcohol. So, but the alcohol is not separate; it's on the same side as the thing. So this is an intramolecular reaction.
Oh, I remember. Yeah. Okay.
Yeah. Uh-huh. Yeah.
When there's a dehydration.
Yeah. So it would be, but
So like temperature was specified.
yeah, it was specified, and we only had alcohol there. Like if this was a primary one, right? Then you know how in Wellington A, like it just attacks itself to like make the symmetrical ether. But if we have an alkene, the alkene is gonna be more basic than the alcohol. So the acid here is gonna protonate the alkene instead of the alcohol, right? And then you know how when we get that carbocation right there, usually some kind of nucleophile like bromine minus chlorine minus water or alcohol attacks it. In this case, we have nothing there. The thing that is here though is that alcohol, where that alcohol can attack that carbocation and form a 1, 2, 3, 4, 5, 6-membered ring. So this is an intramolecular hydration reaction.
Then would it have 3 connections and then this have to leave?
Yeah, yeah.
Would this come and take that extra hydrogen?
Yeah, yeah. That's right. That's right. This is an intramolecular reaction, which is like one of the harder reactions. Yeah.
Okay.
So for this problem here, we have a strong acid and heat. If we have a strong acid, we have to look for our most basic group, which could either be this alcohol or alkene. The alkene is going to be more basic than this oxygen. So we're going to use this as the base. But which carbon specifically is going to grab the H? The left one or the right one? Yeah, to form the more stable carbocation. That's right. So that is going to be like that, and form our carbocation here. Where you know how in previous reactions, once we have the most carbocation, after any rearrangement possibilities, in this case, no rearrangement happens because it's already in its most stable position. Something attacks it, like a Br minus, Cl minus, water or alcohol. We have no water, alcohol, or Br or Cl here, right? But we do have something here within the same molecule as the electrophile, which is an alcohol, right? This alcohol here has two lone pairs of electrons where it could attack that carbocation right there. This is an intramolecular reaction. Intramolecular reaction, which means that the nucleophile is on the same molecule as the electrophile. Same molecule as electrophile. And intramolecular reactions will always form rings or do ring closing. Like it closes a ring. Yeah. Okay. And to keep track of the groups, I always number my attacking atom number 1. And then I always end my numbering system at the electrophile, the atom being attacked. So the atom that's attacking here is that oxygen, which is why I number that number 1. This just helps me like close the ring and see what's attached to what. You could say A, B, C, D as well, but I like numbering it better. So that's 2, 3, 4, 5, 6. I stop here at 6 because that's the atom being attacked. We know that we form a 6-membered ring where one of the atoms of the 6-membered ring is the oxygen atom right there. So let's draw out that template first. I know that we're going to form this 6-membered ring where one of the atoms of the 6-membered ring is that oxygen, and that oxygen is number 1. So let's label that 1, and then label everything else 2, 3, 4, 5, 6. We see here at oxygen is still bonded to hydrogen, which gives the oxygen a positive charge because there are 3 bonds to the oxygen right there. Right. Now, what other groups are we missing on that ring right there? What other groups do I have to add, and on which carbon? Methyl group at carbon 3, that's right. And how about on carbon 6? What is on carbon 6? Yeah, there's 2 groups on the carbon 6, ethyl and a methyl. Okay. Now that's the complete ring closing, where what's the very last step that's going to happen here? Yeah, deprotonation to neutralize the positively charged oxygen. And in this case, we formed a cyclic ether. Yeah, final answer. Intramolecular reaction. There is going to be no water in this reaction. Yeah. Oh yeah. The acid and water would both be. The catalyst doesn't have to be in excess because it keeps getting reformed throughout the mechanism. When reactions, we could keep it in low concentration to just keep the reaction going, because if it's in excess, it could actually like overpower the nucleophile. Oh, that's a good question, because for this intramolecular reaction, if there's multiple ones, it won't necessarily attack the most substituted one. it will attract the one that forms the most stable ring. So let me give you an example of that. Let's say we have this right here. Like, no, H. Three alkenes there, right? Where let's say, let me just erase that because you know how this carbon here is the most substituted one, the one that will give us the most stable carbocation. We don't want this. Actually, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 numbered ring.